Good morning, everyone, and welcome to NAS 304, bringing QUIC, the Secure Transport Protocol, to AWS. My name is Wesley, and I'm presenting today with Cameron. We're both software engineers at AWS, and we're excited today to talk to you about the QUIC Transport Protocol. So today, we're going to start by answering the question, what is a transport protocol? And in particular, what is the QUIC transport protocol? Next, we'll introduce S2N QUIC, AWS's new implementation of the QUIC transport protocol. And finally, we've picked 5 exciting features of QUIC that we'll go over in more detail and contrast them with TCP and TLS. And for each of these features, we're going to talk a little bit about the steps we've taken in S2N QUIC to test performance and functionality. So before we get started talking about the QUIC transport protocol, let's answer the question, what is a transport protocol? A transport protocol is a means for communicating and sending data between hosts in a network, oftentimes between a client and a server. Transport protocols enable applications to send data over a network by providing a structure for that data to be carried in, as well as a basic set of features. Those features might include connection establishment, so that each side of the communication can agree on various configuration and security settings. Reliable ordered delivery of data, so that the peer receives everything that the sender intended. Congestion and flow control, so that the sender doesn't overwhelm the network or the receiver. And these days, we expect our connections to have confidentiality and integrity to protect our data. In terms of network layers, transport protocols sit atop the IP layer. This layer is responsible for routing packets between machines and over the internet. The most well-known and deployed transport protocol out there is TCP, or the Transmission Control Protocol. TCP implements most of the features I mentioned earlier, including connection establishment, reliable data delivery, and congestion and flow control. But there is a big feature missing from TCP, however, and that's encryption. By default, data sent over a TCP connection is unencrypted. And that's why, usually when we talk about TCP, it's deployed with TLS layered on top. TLS provides confidentiality and integrity to TCP connections. And since TLS is so fundamental to the security of data on the internet, AWS has its own implementation of TLS called S2N TLS. On top of all this, we have HTTP, an application protocol that manages the requests and responses for websites and data. Together, TCP and TLS have been the standard for reliable and secure communication on the internet for decades. And that brings us to QUIC. QUIC is a new transport protocol that was standardized in May of 2021. QUIC is built on top of a much simpler transport protocol called UDP. On its own, UDP doesn't provide any of the transport protocol features we've been talking about, so those features are implemented in QUIC. And in contrast to TCP, encryption is incorporated directly into QUIC. QUIC uses TLS to establish encryption and authentication keys, which are used to protect every QUIC packet. And finally, on top of QUIC, we have HTTP 3. HTTP 3 is similar in many ways to its predecessor, but being layered on top of QUIC allows it to benefit from some of the new QUIC features we'll be talking about. Before we dive into the features of QUIC, though, let me introduce the new AWS implementation of QUIC. We call it S2N QUIC. S2N QUIC joins the S2N family of AWS libraries alongside S2N TLS. These libraries work together to keep data in transit secure. And continuing in the tradition of S2N TLS, S2N QUIC is open source. You can check out the source code today on GitHub. And if you check out that source code, you might notice that S2N QUIC is written in Rust, a memory-safe programming language that has the same performance and efficiency characteristics as C, while being much safer to deploy. We're rolling out QUIC and HTTP 3 support in AWS services, starting with Amazon CloudFront. As we dive into the features of QUIC, we'll be talking more about S2N QUIC and how it makes sure that these features are performant and secure. And with that, I'll hand off to Cameron to talk about some of the exciting features of QUIC.
Awesome. Thanks, Wesley. So let's start by comparing how connections are established between two endpoints. So anytime a client wants to talk to a server, it obviously needs to establish a connection with that server. In this process, both sides need to agree on versions that are used in that protocol session and the features that are being used during the lifetime of that connection. We also establish routing information. So when we send packets from one destination to the other, those packets end up at the right place. Let's start by looking at the relatively simple connection establishment flow found in TCP. First, the client sends a SYN packet towards the server, indicating it wants to establish a connection with that particular server. The server then responds with a SYN ACK packet, letting the client know that the connection has been established or accepted. And it is at this point that the client can actually start sending data to the server, along with acknowledging that it received the SYN ACK packet. And this all takes place in a single round trip, which by the name implies is the time it takes for a peer to send a packet and get that packet acknowledged by its peer. However, as Wesley pointed out earlier, the data over this communication channel is not encrypted, meaning it is susceptible to eavesdropping and manipulation. Let's take a look at what it might take to encrypt this communication channel. First, we layer the TLS protocol on top of an existing TCP connection. And by doing this, we gain confidentiality and data integrity. To begin the TLS handshake, the client communicates its desired security configuration for that particular session with the hello message. The server then responds with a set of messages which indicate which settings were chosen for that particular session. The client then follows up to the server's messages with its own set of messages, indicating that it has finished the handshake. Finally, the server responds with its own set of final messages, at which point the server is finally done with its handshake. And finally, at this point, the client can start sending data to the server and exchanging application data. And it's all encrypted. And this is great, but as we can see here, there's a bit of an issue. The messages going back and forth kind of adds up. As you can see, there's 3 round trips required to establish this connection. To be precise, it is 3 times as much as what it takes for a TCP connection to be established. And this can really add up in networks with high latency. As an illustration, if round trip time is 500 milliseconds, it takes a whole second more than a TCP connection to start interacting with the application. Luckily, we can improve this situation a bit by using the latest specification of TLS 1.3. Again, we layer the TLS handshake on top of an existing TCP connection. And in addition to the initial client hello message, it includes the key share extension. This subtle change allows the server to follow up with several messages, at which point the client is finally ready to start sending encrypted data. As you can see, TLS 1.3, we are able to cut out a full round trip from TLS 1.2, leading to a better user experience. And as a benefit, we're still encrypting the connection. However, we're not still where we were with TCP, right? We still need an extra round trip to establish this connection. And this is one of the problems QUIC tries to address. Let's take a look. As you can see, the client starts by sending an initial packet, which contains the first round of messages from the TLS layer, which is the TLS 1.3 handshake. The server responds with an ACK and the next round of messages from the TLS layer on the server side. And that's actually it. At this point, the connection has been fully established and is ready to start transferring data between the 2 endpoints. And this all takes place in a single round trip. If we look back at the comparison table, we can see that we have the same number of round trips it took to establish a TCP connection, all while being completely encrypted and protected. Because we're able to start encrypting and transferring data earlier, applications should feel more responsive, especially when new connections need to be established in order to make forward progress. Now that we know what we should be observing in theory, we do want to ensure that in practice, S2N behaves correctly. For this, we built a tool that allows us to perform benchmarking scenarios in a controlled environment and then compare those scenarios and implementations of various transport protocols. One of the scenarios we test is where the client repeatedly connects to a server and then closes the connection afterwards. We can measure the results and get a connection establishment rate and then graph and visualize the differences. First, we use TCP as a baseline, since we know that it requires a single round trip to establish the connection, as we saw earlier. The green line here shows how many connections we can establish per second, and the higher the value, the better the perceived performance of our application. Next, if we look at TLS, and see that the measured rate is a third of that of TCP, which is exactly what we would expect, given that it requires 3 round trips to establish the connection. If we look at TLS 1.3, we also see that it is improved over the previous versions of TLS 1.2 and earlier. However, it's still not where it is with TCP, about half of what TCP is able to do. Lastly, we can measure S2N Quick and see that it actually matches that of TCP. This means that our implementation correctly translates theory into practice. This is just one of many examples that we are able to execute with our benchmarking tool. This helps keep the bar high. Let's take a look at our next feature. I think it's safe to say everyone here cares about the confidentiality and integrity of their data. Particularly with data sent over the internet, we don't want malicious attackers to be able to inspect or manipulate the data contained within the packet that we send and receive. On top of that, we'd rather make it difficult for others to track our online activity. Let's compare our options on how we accomplish that. As we commented earlier, none of TCP is encrypted or safe from manipulation. The chart here shows a TCP header layout or a packet layout. As you can see, there's quite a bit of data and metadata exposed in the header here. And the payload being transmitted is in clear text. These packets are sent over the network between the client and the server. This means that each one of the fields that you see in this packet can be viewed, collected, and/or changed by an on-path attacker. In this scenario, neither the client nor the server would have any idea that this attack is taking place. Not good. The lack of packet authentication also leaves the connection open to session hijacking, which is where an off-path attacker guesses a few of these fields in the packet, namely the ports and sequence number, and injects spoof packets into the flow of one of the receivers. This corrupts the communication between the two endpoints and leads to problematic situations, we'll say. Now, this does require guessing these fields, like I mentioned, which can be a bit difficult, but it's not impossible. Again, the client nor the server would have any idea that this attack is taking place. When we layer TLS on top of TCP, we go a long way towards ensuring confidentiality and data integrity of our packets. TLS is able to encrypt the payload and the data contained inside of the packet. This prevents it from being modified by authenticating the contained bytes. However, it does still leave everything outside of that payload open to eavesdropping or manipulation. An attacker could inject their own packets or manipulate anything outside of this and not be detected. One example of an attack like this is a reset attack. This works by guessing a few of these fields, namely the ports and the sequence number in the header, and then sending a reset packet towards one of the receivers. This will cause the connection to be immediately closed, even though neither side actually wanted this to take place. This results in a denial of service. With all of this in mind, let's take a look at the quick packet layout. First, encryption in QUIC is not optional or layered, as it is in TCP. Rather, TLS is embedded inside of QUIC. Also, encryption must be established using TLS 1.3, bringing all of the security improvements that it offers, like required forward secrecy and full handshake signatures. Second, because TLS is incorporated into the QUIC protocol rather than being layered on top, the QUIC packet itself is authenticated and fully encrypted, with the exception of the destination connection ID that you see there. This means that outside of routing information, application data is completely private. It also makes it practically impossible to spoof a valid QUIC packet without knowing the connection's encryption keys. One thing that I do want to bring up here is that with the increased privacy that QUIC offers, it does bring some unique challenges to existing firewalls and network analysis tools. Because all of these QUIC packets are encrypted, metadata inspection and analysis becomes difficult or impossible. For example, with TCP, a network analyzer could track the amount of loss that occurs on a connection by inspecting the ACK packets that are sent in between. This is not at all viable with QUIC, as all of the ACK frames are inside of the encrypted payload. Additionally, the destination connection ID, even though it is in the open, can change periodically throughout the lifetime of the connection. All of this does make privacy a lot better, but it does make performing connection flow analysis more difficult. Luckily, there is still some good news here. Because QUIC itself is built on top of UDP, existing firewall rules and filters that are built for UDP will continue to apply. Similarly, HTTP 3 builds on top of the existing HTTP semantics. This means that web application firewalls that use these semantics to mitigate attacks will continue to function as well. Firewalls that wish to inspect connections based on the TLS hello messages that are exchanged, namely the server name extension and others, can continue to do so as long as they are updated to understand the QUIC packet layout. As with most standards these days, QUIC itself is specified in an RFC, or request for comments, which is adopted by IETF, the Internet Engineering Task Force. In fact, QUIC is specified in 3 separate RFCs, each containing hundreds of requirements that must be implemented to work properly. There are many requirements related to security and protection of packets that S2N QUIC must implement correctly for all of the security features that we've talked about to work. To help us make sure that we didn't miss any of these critical requirements, we developed a tool to help us track compliance with all of the requirements from the RFC. As we implement each requirement in code, we annotate the code with a citation from the RFC, linking back to the section and indicating why the code is there. The tool then takes these citations and matches it up with text from the RFC and generates a report. The underlined sentence you see here in the image represents a requirement from the RFC. If you click on that requirement, it takes you to the line in the S2N QUIC source code where the requirement is both implemented and tested. One really nice benefit to all of this is that the S2N QUIC codebase can be understood and explored through the RFC itself. This makes it very easy for S2N Quick to perform an audit against all of the requirements that it implements. And as with all of our checks, every time we make a code change in S2N Quick, this report is built, and that tracks the requirements that have been implemented and then the ones that are still remaining to be. All right, next feature. Next, we'll take a look at the application level features that Quick provides to make it easier to parallelize streams of data on a single connection. In other words, stream multiplexing. Modern web applications and web pages perform many, many requests to provide rich interactions for users. As an example, just opening the front page on Amazon.com, hundreds of requests are performed to access images and various resources to provide a good user experience. Ensuring that each one of these requests completes quickly as possible is absolutely critical to providing the best user experience for visitors to the site. Traditionally, with TCP, to enable parallel requests, multiple connections are established with the client and the server. In this example, we have a connection for each request: the script, the style, and the image. And this is a relatively straightforward solution. It doesn't require any new protocols to be defined or any additional infrastructure to support. However, as we discussed earlier, establishing each one of these connections can take some time and add latency and delay interactivity in our application. And this all especially adds up if we start encrypting this data. It also has the downside of not sharing any bandwidth information between each one of these connections. This leads to each connection requiring to compete against each other for network resources. And this all makes it very difficult to establish relative priorities between the application's requests, leading to a potentially suboptimal response pattern from the server. One way that we can overcome some of these issues is to frame streams on top of a single connection. Here, the client receives small chunks of each one of the requested resources from the server. This means that we only have to establish one connection and pay that cost once, and then we can make several requests at a time. Also, because we now have some framing around requests, we can build in a mechanism to prioritize which chunks are sent by the server. And all of these concepts are present in the specification of HTTP 2. This solution solves the problems that we introduced earlier with opening multiple connections. However, it really isn't able to do so without introducing some new issues. Let's consider what exactly happens when a packet containing, for example, the image data is lost on this particular connection. Because the TCP stream is globally ordered and has no concept of the frames that we've applied to this particular stream, all of the packets behind that lost packet are completely blocked and cannot make forward progress until that lost packet is retransmitted and received. And this is what is known as the head-of-line blocking problem. Another tricky problem this introduces is we now have flow control and framing to consider. And this brings additional complexity and forces each new application protocol layered on top of TCP to reinvent these same mechanisms over and over again. Let's take a look at how Quick attempts to solve these issues. With Quick, we move the stream multiplexing logic into the transport layer. As before, we can make multiple requests on a single connection. However, now with the QUIC layer handling the multiplexing logic for us, the requests all perform in parallel. QUIC is aware of the stream frames that are sent between the peers, and even though, let's say, a script JS packet is lost, the style and the image requests continue to make forward progress. The application protocol itself is greatly simplified now and only really needs to concern itself with reading and writing from these streams through the provided QUIC API. The QUIC layer takes care of all of the stream framing and flow control mechanisms, making it straightforward to build new and rich application protocols on top. The latest specification of HTTP 3 does exactly this. Now, even though the application protocol is greatly simplified, moving it into the transport protocol can become quite complicated and has subtle edge cases that need to be considered. For this reason, we've invested a lot in automated testing in S2N QUIC. This ensures all stream operations are correctly processed. The screenshot here shows just a few of the many checks that we run as part of our continuous testing suite each time we make a code change. One testing method that I do want to highlight here is API fuzzing. In this method, we have an S2N QUIC client connect to an S2N QUIC server. Both endpoints call stream functions at random and ensure all of the invariants are preserved. If any invariants are violated during this exchange, the sequence of events is dumped to disk and can be replayed to make it easy to investigate why the failure occurred. By randomly exploring combinations of API calls, we're able to identify edge cases and issues quickly, all before merging these changes into mainline. Now let's hear from Wesley again about some additional features in QUIC.
Cool. Thanks, Cameron. So as we've seen so far today, QUIC has a lot of great features. But in order for QUIC to be a suitable alternative to TCP, it needs to have great performance as well. And not just under ideal network conditions, but also when the network is congested or unreliable. This is where the congestion controller in QUIC comes into play. A QUIC connection may operate under many different networks with different characteristics. You might have a connection that has to pass through many different routers over long distances, resulting in long round-trip times for a packet to be sent from the client to the server and back. Your connection might be competing with many other connections on the same network path. Or the network path could be unreliable, frequently dropping packets or corrupting them. The job of the congestion controller is to try to figure out how much bandwidth a network can sustain, given a diverse array of network conditions such as these. Congestion controllers generally work by increasing or decreasing the amount of data an endpoint can send in response to signals from the transport protocol. When the transport protocol is sending positive signals, such as acknowledgements of packets, the sending rate is allowed to increase, as this could be an indication that the network can sustain higher bandwidth. When the transport protocol is sending a negative signal, such as a lost packet, the sending rate is decreased, as this could indicate that the network is facing some congestion. This process continues as additional signals arrive and the congestion controller tries to find a stable bandwidth. There are many different congestion controllers out there, each with different techniques and strategies for fairly maximizing throughput. QUIC is free to use any congestion controller algorithm, and we can even develop new algorithms to target specific use cases or to attempt to improve performance through new methods. These congestion controllers may operate differently, but they all have in common that they rely on signals from the transport protocol to decide how to react and avoid further congestion. QUIC makes several improvements to over TCP on the signals it can provide to the congestion controller. In TCP, a receiver must infer the order that a packet was transmitted, making it harder to tell if a packet was actually lost or just delayed or reordered. In QUIC, every packet is assigned a strictly increasing packet number that explicitly indicates the order in which a packet was transmitted. Since QUIC knows the order of packet transmission, it can provide a more accurate loss signal to the congestion controller. Another important signal that congestion controllers use are the acknowledgments from the peer on whether a packet had been received or not. In TCP, it's limited in how many different ranges of different packets can be acknowledged at once, whereas QUIC has a much higher limit. Again, this is another improvement to packet loss signals, particularly in high loss networks. And finally, the measurement of the round trip time it takes a packet to be received and acknowledged is another important signal to the congestion controller. With TCP, this signal can be distorted when acknowledgments are delayed, while QUIC explicitly communicates delay to the round trip time, allowing again for a more accurate measurement. Of course, over the years, various attempts have been made in TCP to try to improve these signals to varying degrees of success. QUIC has learned from these attempts and includes them in the protocol by default. Overall, the improvements to these signals allow any congestion controller that is used to more accurately estimate the network bandwidth, which ultimately leads to better performance. Beyond just the improvements to these signals, the QUIC protocol is actually flexible enough to allow new signals to be introduced. And we've designed S2N QUIC in a way to make it easy to experiment with new and better congestion controllers. But experimenting and innovating with new signals and congestion controllers, it has the potential to improve performance, but it also brings additional testing burden. Namely, we need to be able to simulate and measure the performance impact of our experiments. To facilitate this, S2N QUIC includes several simulation tools. First, we have the Congestion Controller Simulator, which plots the growth of the congestion window over time under various network simulations. The fluctuations you see in this green curve show the congestion controller changing the amount of in-flight data in response to simulated packet loss or acknowledgments. We generate plots like these on every S2N QUIC code change, which helps us to understand the impact of any changes we make to the congestion controller. As we iterate on existing congestion controllers and introduce new ones, we can theorize on how to improve performance, But we also need to make sure that that theory is supported and confirmed by concrete data. And given how we saw congestion controllers must operate under many different network conditions, that data should reflect a wide range of conditions as well. For this reason, we developed a Monte Carlo simulation tool. This tool lets us execute thousands of randomized simulations that vary one or more input variables, such as the maximum bandwidth of the simulated network. From this output, we get a visual representation of the relationship between the input variables and overall performance. As with the congestion controller simulator, this helps us to understand the impact of congestion controller changes, with the added benefit of being simulated over thousands of varying conditions. Together, these tools help us to experiment and monitor the performance of the congestion controller. Next, I'd like to talk about a feature that's not found in TCP. It's called connection migration. To illustrate why this feature was developed for QUIC, consider this common scenario. You're listening to some music streaming over your home Wi-Fi network, and you decide to go for a walk outside. At this point, your connection to your Wi-Fi network terminates, and your phone starts connecting to a 5G cell tower. The connection via the cell tower has a different IP address and port assigned, so the server doesn't recognize this new connection. At this point, the connection must perform a full TCP and TLS handshake. And as we saw earlier, establishing a new TCP and TLS connection could take a full second or longer, additional overhead that we'd really like to avoid. When the new connection is finally established, data can start flowing again. But there's a good chance during the transition that the music ran out of buffer and skipped or stopped playing altogether. This is one of several scenarios that QUIC's connection migration feature has been designed to address. The key difference of why a TCP connection cannot survive moving from Wi-Fi to 5G and QUIC can is how a connection is uniquely identified. In QUIC, connections are identified by a unique ID completely independent of IP address. Both the client and the server use these connection IDs for sending and receiving packets. When your phone moves from Wi-Fi to 5G, the IP address still changes, but the QUIC connection ID on packets stays the same. As packets flow over the new path between the client and server, each endpoint recognizes this stable connection ID and can route and process packets without forcing a new connection to be established. The original connection has migrated with no interruption to the music. Now, this is a great feature to have, but it brings with it additional security considerations. S2 and QUIC must ensure that packets coming from a new IP address aren't just being copied or forwarded by an attacker, or that the IP address isn't being spoofed by an attacker. These attacks are mitigated by a mechanism in QUIC called path validation. Path validation works by forcing the client to verify their IP address by repeating some unpredictable data back to the server. The server sends the unpredictable data encrypted as part of a path challenge to the new IP address. And a valid client at that address will decrypt the challenge and repeat the data inside back to the server in a path response. In the case of an attacker, they won't have the encryption keys necessary to decrypt the path challenge. So the connection migration to the attacker's IP address is canceled. This mechanism allows QUIC to safely allow for connection migration without compromising on security. Like many of the features we saw today, connection migration is a complicated mechanism that must be implemented correctly to work properly. But it's not just enough for it to work between an S2N QUIC client and an S2N QUIC server. There are many other QUIC clients and servers out there, and we want connection migration and all the other QUIC features to work between those implementations as well. To ensure S2N QUIC works with these other QUIC implementations, we execute a suite of almost 20 different feature tests between S2N QUIC and each of these implementations. These tests are run on every time we make a code change to S2N QUIC, whether it's a new feature or a minor fix or configuration change. These tests ensure that all of the features that we've talked about today continue to work well with all the other QUIC implementations. Now, to wrap things up, I'll hand back to Cameron.
Awesome. So in summary, today we've discussed how QUIC connections are established with very minimal latency compared to TCP and TLS, how confidentiality and data integrity of QUIC packets is maintained throughout the lifetime of the connection and leads to enhanced security and privacy. We look at how QUIC provides stream multiplexing mechanisms to ensure parallel requests are efficiently processed, all without blocking each other, all leading to a better user experience. We saw that QUIC's congestion and recovery signals enable better detection of loss and bandwidth constraints of the network that they're being executed on. And lastly, really exciting new features of QUIC, which is able to provide connection migration, which is a very important aspect to an ever-increasing mobile world. We also looked at how S2N QUIC uses all of these various testing methods to ensure that each one of these new features and enhancements are delivered with stability and performance. Through S2N QUIC, beginning with CloudFront, AWS will offer QUIC capabilities to customers to empower the next generation of applications and experiences. As we mentioned earlier, S2N QUIC is open source and developed on GitHub. Please feel free to take a look at the code and let us know what exciting new applications you end up building with it. Thanks for joining us.